Hello everyone, welcome to our presentation. My name is Ömer Faruk Öncel and my friend's name is Yusuf Ona. Today we will talk about a hybrid crypto system with RSA and AES. Firstly, Yusuf will start by giving some brief information about cryptography, then he will explain RSA and some attack types on RSA. Then I will give a quick overview of hybrid cryptography. I will explain the AES crypto system and square attack on AES. At the end of our presentation, Yusuf and I will try to communicate with this hybrid crypto system. Let's start.
Hello everyone, I'm Yusuf. I will start by giving some brief information about cryptography and then I will explain the RSA crypto system and its example. Then some attack types on RSA. What is cryptography? Cryptography or encryption is all of the methods used to transform the information contained in a readable data into a form that cannot be understood by undesirable parties. Cryptography is a set of mathematical methods and is intended to provide conditions such as confidentiality, authenticity, and identity control necessary for the security of important information. These methods aim to protect information from active attacks or passive detection that may be encountered during the transmission and storage period of information. And what is RSA? RSA is a type of public key encryption method that relies on the algorithmic difficulty of factoring integers. It was discovered by Ron Rivas, I.D. Shamir, and Leonard Edelman in 1978. And the word RSA comes from the surname of those who found it. An RSA user generates the product of two large prime numbers and declares on the public key along with another value his choice. It stores the selected prime factors. Someone using the public key can encrypt any message, but only the person who knows the prime factors can decrypt it. And how does RSA work? The RSA algorithm consists of three steps. These are 1. Key generation, 2. Encryption, and 3. Decryption. Now let's talk about key generation. RSA requires a public key and private key. The public key is known to everyone and is used to encrypt the message. A message encrypted with a public key can only be decrypted with a private key. And it doesn't matter if the public keys are known to everyone, but private keys, as the name suggests, must remain private. RSA keys are generated like this. Step 1. We choose two different prime numbers. We call them P and the other is Q. For safety reasons, the number P and Q should be chosen randomly and should be at close distance from each other. Step 2. We calculate n number. N equal P times Q and n is used as a modulus for both the public and private keys. Step 3. We calculate torsion number. Torsion number equal P minus 1 times Q minus 1. Step 4. We will choose one integer and then call it E. But this number we will choose should be in following rules. Rule 1. 1 smaller than E and E smaller than torsion number. And E and torsion is co-prime. And our E number is the public key. Step 5. Now we will determine the number D and we calculate this number as follows. D times E equal 1 mod torsion and D is stored as a private key. And now our public keys are N and E and our private keys are P, Q, D and torsion number. And now let's talk about the encryption. Suppose we have a text or number to encrypt. Encrypting the number is simple because we are dealing with numbers. But to encrypt text, we need to use a protocol that converts to text to numbers. After doing this, we calculate the encrypted message as follows. 1. Let's call the encrypted message C. C equal m power e mod n. So we found our encrypted message. Let's talk about the decryption. The other person needs to have a private keys. This decrypts the C encrypted message we sent. You remember the number M. This number was the first unencrypted number. So M equal C power D mod M. So we decrypt our message. Here is an example. Now let's show all we have learned with an example. Let's choose two different prime numbers. Let one of them be 61 and the other 57. P equal 61 and Q equal 57. Now let's calculate n number. You know n equal P times Q and n equal 61 times 57. 32, 33. Now let's calculate the number torsion. Torsion equal P minus 1 and Q minus 1. So torsion is 60 times 56. So torsion number is 31, 20. Now let's choose a number E. You know torsion and E must be coprime. Let's choose E equal 17. Now let's find the number D. D times E equal 1 mod torsion. So D times 17 equal 1 mod 31, 20. So D number is 2753. So we found all our numbers, public keys, and equal 32, 33, E is 17, and private keys are P, Q, D, and torsion. Let number M to be encrypted be 65. We encrypt it like this. C equal M power E mod n. So number C equal 2790. And then when we send the message, the other person decrypt the message as follows: M equal C power D and mod n. So M is 65. And yes, we have decrypted the encrypted message. And now let's talk a little bit about attacks on the RSA encryption system. One, if the number E we choose is a small number and the message to be encrypted is also small number, it can be easily deciphered by taking E roots of the encrypted message. For this, our number must be chosen in large numbers. 2. If many messages are encrypted and sent with the same E and N numbers, these messages can be easily decrypted with the Chinese remainder theorem. For RSA, we usually use 200 or 300 digits prime numbers. The reasons for this to increase security and make the encrypted message impossible to decrypt. But let's not forget that private keys shouldn't be known to others. It is useful to communicate this using other secure means. And as you know it doesn't matter 200 or 300 digit prime numbers are used if these private keys are found by others.
Thank you, Yusuf. Now, I will move on to hybrid cryptography and advanced encryption standard. Hybrid cryptography is a concept that merges two cryptosystems into one scheme. One of the cryptosystems is public key cryptosystem and other one is secret key cryptosystem. Secret key cryptosystems are more efficient than public key cryptosystems because in public key cryptosystems there are lots of mathematical operations to handle. The reason for that is to provide security while sharing the key in public. The disadvantage of secret key cryptosystems is that we are unable to share our secret key in public. Before communication starts, the receiver and sender should communicate for sharing the key in a secure channel. As I mentioned earlier, hybrid crypto systems provide two advantages. One is speed, and the other is the removal of the secure channels in communication. The sender and receiver cannot always share the key. Can you imagine that the receiver lives in Canada, meanwhile the sender lives in USA? There is no way to share the secret key in a secure channel before communication starts. That's why hybrid crypto systems are needed. Now, I move on advanced encryption standard. AES is a secret key crypto system, which means it needs a prior communication for sharing the key. It is an iterated cipher, and the number of its rounds depend on the length of the key. If the key length is 128 bits, the number of its rounds is 10. If the key length is 192 bits, the number of its rounds is 12. If the key length is 256 bits, the number of its rounds is 14. The algorithm contains 4 steps per round, and they are called add round key, substitution bytes, shift rows, and mix columns consecutively. In add round key step, a 128-bit round key that has been stamped from the main key schedule is XORed state, which means we are applying XOR operations in hexadecimal numbers. In substitution byte steps, each element of state matrix is replaced with the elements in SBox. For instance, if state matrix contains A7, it will be replaced by DA. This creates a nonlinear confusion in data. Shift rows and mix columns are the sublayers of diffusion layer. In shift row sublayer, rows of matrix are permuted. The first row stays same. The second row is shifted to the left by 1. Third row is shifted to the left by 2. And fourth and last row is shifted to the left by 3. All these shiftings cause diffusion of the bits. In mix column sublayer, the matrix occurring after shift rows operation is multiplied by a 4 by 4 matrix which contains 02, 03, 01, and 01 as its first row, 01, 02, 03, and 01 as its second row, 01, 01, 02, and 03 as its third row, and 03, 01, 01, and 02 as its fourth row. All these steps are applied to our plaintext, which is converted to the 16 bytes hexadecimal plaintext. The loop continues 10 times for 128-bit key length, 12 times for 192-bit key length, and 14 times for 256-bit key length. Very last step does not contain mix column operation. For decryption process, we should apply at round key, inverse substitution bytes, inverse shift rows, and inverse mix columns operation for 10 times if we are using 128 k length. In inverse substitution bytes step, we should use inverse SBox to substitute the elements in matrices. In inverse shift row sublayer, rows of matrix are permuted oppositely. The first row stays same. Second row is shifted to the right by 1. Third row is shifted to the right by 2. And fourth and last row is shifted to the right by 3. As I mentioned earlier, in the mix column operation, in the shift rows operation, we were shifting to the left. Now, when we are decrypting the ciphertext, we are using the inverse shift rows operation, and we are shifting to the elements to the right. In inverse mix column operation, we are doing same Galois multiplication operation with different matrix. Now our matrix contains 0E, 0B, 0D, and 09 as its first row, 09, 0E, 0B, and 0D as its second row, 0D, 09, 0E, and 0B as its third row, and 0B, 0D, 09, and 0E as its fourth row. After all operations applied, we get the plain text, which means original message back. Now, when we are look at the figure, we can see that we have a plain text. Plain text is converted to 16 bytes hexadecimal plain text. Then we are starting to apply encryption operation. Firstly, we are applying at round key. In this step, we are using round k0, and we are XORing the plain text and at round key together. Then we are starting to iterate this cipher, which means we are starting with substitution bytes, then we are applying shift rows operation, then we are applying mixed columns operation, and we are applying at round k operation. These operations are applied 10 times for 128 kbit length, for 12 times for 192 kbit length, and for 14 times for 256 kbit length. After all this step applied, in the very last round, we don't have mixed columns operation. Then we get the ciphertext. For the decryption process, now we are going back. If we say that we used bottom-up approach in encryption, we use top-down approach in the decryption. We have a ciphertext, which is encrypted. Then we are using at round k operation. Now, in the iteration steps, which means in loop, we are using inverse shift rows, inverse substitution bytes, inverse mixed columns, and at round k. We are using at round k instead of inverse at round k because the XOR operations are equal to its inverse. In the very last round, we are using inverse shift rows, inverse substitution bytes, and at round k. And we don't have inverse mixed columns in here, as we don't have in the encryption part. Now, I want to give an example on 128-bit k-length AES encryption and decryption. We have a key in English, and that's my kung fu. It is 16 ASCII characters, 1 byte for each. 1 byte is equal to the 8 bits. If we multiply 16 by 8, we get 128. That's why we will do 10 operations. Our k is translated into hexadecimal. Then we get hexadecimal k string or k array. We have plain text in English 2192. It is also 16 bytes as 16 bytes, which means 128 bits. And we are translating into hexadecimal plain text. Then we need to do k expansion operations. We need to get 10 round key. How do we do that? In here we have k in hexadecimal, 128 bits. We are splitting up into 4 sub-array. Then we have W0, W1, W2, and W3. We are getting the last sub-array, which means W3, and we are applying circular byte left shift of W3 by 1 to the left, byte substitution from SBox, and adding round constant. Round constant will be changed in each expansion step. In here 0, 1, 0, 0, 0, 0, 0, 0. In the next step it will be 0, 2, 0, 0, 0, 0, 0. It will go like that. Then we need to calculate 4 sub-arrays. How do we do that? We are getting W0 and new W3 and XOR them and store into them W4. Then we are getting W4 and W1. We are XORing them and storing W5. We are getting W5 and W2 arrays and we are XORing them. Then we are storing into W6 and we are getting W6 and W3, not new W3, be careful, the old W3, and we are XORing them and we get W7. Then we are merging these new 4 subarrays and getting first round key. We are applying 10 times exactly same operations and we get round 1, round 2, round 3, round 4, round 5, 6, 7, 8, 9, 10 round keys. Then we are starting to encrypt our plaintext. In round 0, we have just one operation. This is at round key. We are getting state matrix and we are getting round key number 0 matrix and we are XORing them. Then in round 1 we have substitution bytes, we have at round key matrix, the last matrix, and we are substitute bytes from SBox and this leads to a new state matrix. Then we are doing shift row operation. As you remember, first row stays same, like here. Second row is shifted to the left by 1. Third row is shifted to the left by 2. And fourth and last row is shifted to the left by 3. This leads a linear mixing step, diffusion, nonlinear diffusion. Then we have mixed column operation. As I mentioned, we have fixed matrix for mixed column operation and we are multiplying this matrix with the state matrix. But in here the multiplication is done over Galois field. We have Galois multiplications. Then at the for the last operation we are doing at round k again. We are getting state matrix after mixed column operation and we are at round key number 1 and we are XORing to these two matrices. Because of we are in the round 1, we are getting round k number 1 matrix and XOR with the state matrix. This XOR yields a new state matrix. Then we say that this is the first output of the AES. Then we are doing same operations in a same order. Substitution bytes, shift rows, mixed columns, and at round key operations in each round. In round 2, in round 3, in the same order, in round 4, in the same order, in round 5, in the same order, in round 6, in the same order, in round 7, in the same order, in round 8, in the same order, in round 9, in the same order, but in round 10, we are doing substitution bytes, then shift rows operation, then we don't have mixed columns operation. We are just using at round k operation in this step. And after this step applied, we have ciphertext. If we want to talk about how we decrypt the message, we are, as I mentioned above, as I mentioned before, we had inverse substitution bytes, inverse mixed columns, and inverse shift rows operation, and at round k operation is inverse itself. That's why we are using at round k operation. We are applying top down approach and getting plain text back. We are using ciphertext, then we have at round k operation, we are adding round k10, and we are using shift rows operation, substitution bytes operation, and we are using the same operations in the same order, and we are going to up round 8, round 7. Now we are just going back round 6, round 5, round 4, round 3, round 2, and round 1. We don't have mixed column operation, and we get the plain text back as in here 2, 1, 9, 2. I introduced you AES crypto system and its working principle. I tried to show an example for encryption and decryption. Now I will talk about square attack on AES. If we consider two texts with an XOR difference in 1 byte, this difference will expand in a known way. The XOR difference after one round will show that one column of its matrix has a non-zero difference. This property will then also be propagated to all bytes in the matrix after the second round. Therefore, it is impossible for the XOR difference between two such plain texts to be zero in any byte after two turns. This feature is also used to create an attack called a square attack. Consider 256 different plain texts equal to the 15 bytes. After the two rounds of AES have been calculated, the property described above will apply across all possible pairs. In other words, that byte in each index will contain one of each possible value across all 256 intermediate states. The XOR sum of 256 bytes in each index will therefore equal 0. With this approach, AES crypto system can be broken down.